If you kept stacking neutrons, nothing else. No charge, no atoms, no light. How long could you keep going before reality itself began to break? Somewhere in that fragile balance between quantum rules and gravity's pull, there lies a boundary. A quiet place where matter can no longer obey, and the fabric of space begins to fold under its own weight. Tonight, let's drift there together. To that still frontier where the smallest particles reveal the hidden strength of stars and the beginnings of everything we know. And if this quiet journey brings you even a small sense of wonder, a gentle tap on subscribe means more to me than you might imagine. It helps keep these stories softly alive among the stars. Now, let's begin. Part 1. What happens if you build an object made only of neutrons? If you tried to build an object made only of neutrons? No protons, no electrons, no atoms, at all. How many could you stack before the universe itself says stop? It sounds simple, almost like a thought experiment you could sketch on a napkin. But this single question reaches into one of the deepest frontiers of modern physics. The invisible line where quantum mechanics and gravity collide. Neutrons are peculiar creatures. Each one is a tiny bundle of 3 quarks. 1 up quark and 2 down quarks, bound together by the strong nuclear force, a force so intense that even the most powerful magnetic field in the universe looks gentle by comparison. They carry no electric charge, which makes them unlike protons or electrons. That neutrality tempts us to imagine stacking them endlessly, one upon another, since there's no repulsion to stop the pile. But in the quiet language of nature, neutrality doesn't mean freedom. It hides new boundaries instead. Let's take the idea seriously. If we place a single neutron down, it's fine. 2 can exist close together. For a brief instant, they form what nuclear physicists call a dineutron, but it's unstable, disintegrating in less than a second. 3 neutrons, they scatter apart again. Only when neutrons live inside the dense interior of an atomic nucleus, surrounded by protons, do they find some sense of stability. That's already our first clue. Nature resists pure neutron matter at small scales. Still, scientists wanted to know, is there any way to make it work? In laboratories such as the Oak Ridge National Laboratory in the United States and the European Organization for Nuclear Research, CERN, beams of high-energy particles have tried to simulate pure neutron assemblies. Every experiment has reached the same outcome. Neutrons on their own decay with a half-life of about 880 seconds. That means if you somehow trapped 1 billion neutrons, half of them would turn into protons, electrons, and antineutrinos in about 15 minutes. This is called beta decay, and it's nature's way of restoring charge balance. But what if you keep adding them faster than they can decay? What if gravity joins the game? At that point, things get fascinating and dangerous. Because when neutrons are packed tighter and tighter, each one is forced into higher energy states due to the Pauli exclusion principle, the rule that no 2 fermions can share the same quantum state. The denser the pile, the more violent the quantum pressure pushing back becomes. It's like trying to seat too many guests at a table. Once every chair is taken, newcomers have to stand on the table itself. In physics, this quantum pressure is called degeneracy pressure. It's not emotional, it's mathematical. an invisible push that resists compression even when temperatures drop near absolute zero. In ordinary atoms, this principle keeps electrons from collapsing into the nucleus. But in our thought experiment, with no electrons left, only neutrons, the same principle works one layer deeper, inside the atomic heart itself. At first, that pressure holds steady. But once the number of neutrons grows past a certain threshold, gravity starts to whisper back. Every neutron adds not only mass but curvature. Space-time itself begins to bend. This is where Newtonian intuition fails, and Einstein's general relativity steps in. Einstein's field equations tell us that mass tells space-time how to curve, and space-time tells mass how to move. When enough neutrons cluster together, somewhere around the mass of our Sun, compressed into a sphere about 12 kilometers wide, that curvature traps even light. The transition from scattered neutrons to a solid neutron object is not gradual. It's abrupt, almost catastrophic. First, gravity squeezes electrons and protons together, creating more neutrons through the reaction P plus E minus N plus Nu plus. Then, once enough neutrons are produced, the matter becomes opaque, dense, and self-supporting through degeneracy pressure. This process was first proposed in 1934 by physicists Walter Beatty and Fritz Zwicky, who coined the term neutron star. They suggested that such stars could form in the aftermath of a supernova explosion, the violent death of a massive star. It was an audacious idea at the time, when even the concept of subatomic particles was still new. But decades later, in 1967, astronomers Jocelyn Bell Bernal and Anthony Hewish detected the first pulsar, a neutron star spinning so fast it sent radio pulses toward Earth every 1.337 seconds. It was proof that nature herself had found a way to build the very thing we imagined. An object made almost entirely of neutrons. Inside such a star, the density is almost 10 to the power of 18 kilograms per cubic meter. About the mass of a mountain, squeezed into a single teaspoon. Neutrons there are packed so tightly that their edges blur. They may even dissolve into a sea of quarks, forming what physicists call quark matter. That's one of the most extreme states known to science, a form of matter so dense it behaves as a single quantum fluid. But our question remains, how many neutrons can you stack before reality breaks? The answer lies at the intersection of two competing rules: quantum exclusion pushing outward and gravity pulling inward. For a while, quantum pressure wins, but if you keep adding mass, somewhere around 2.3 to 2.9 solar masses, depending on the nuclear equation of state, gravity finally overwhelms everything. This critical threshold is known as the Tolman-Oppenheimer-Volkoff limit, named after the physicists who calculated it in 1939. Beyond that limit, no force in nature can resist collapse. Neutrons are crushed beyond recognition. Space-time curves until it closes upon itself, and a black hole is born. As the physicist John Wheeler famously said, black holes have no hair. That means all internal structure. Every neutron, every detail, is erased. The line where neutron object ends and black hole begins is one of the sharpest boundaries known in physics, yet no human instrument has ever witnessed it directly. Telescopes like NASA's Chandra X-ray Observatory, ESA's XMM Newton, and the James Webb Space Telescope have captured light from neutron stars only seconds after birth. Some show temperatures above 1 million Kelvin, Others reveal magnetic fields 1,000,000,000,000 times stronger than Earth's. And still, in all their violence, they remain some of the most precise natural clocks in the cosmos, spinning hundreds of times per second without losing rhythm. At the core of each lies the same question we began with. Can pure neutrons form stable matter? Or are they destined to decay, collapse, or dissolve under their own weight? The evidence suggests there is a limit, and it's not negotiable. Reality breaks first at the quantum level, then at the gravitational one. It's humbling to realize that the smallest and most familiar components of atoms, when scaled up, no longer behave as we expect. In the micro world, neutrons are tame, one of the quiet building blocks of every nucleus. But in the macro world, when billions of billions of them gather, they unleash phenomena so extreme that space and time themselves begin to deform. The boundary between these two domains, where quantum rules meet general relativity, remains one of the most important unsolved problems in physics. That's why scientists today are still searching for signs of exotic stars, objects that might bridge the gap. Some hypotheses include quark stars, hybrid stars, and strange matter configurations predicted by the equations of quantum chromodynamics. If one could be confirmed, it would provide the first real glimpse of matter beyond neutron degeneracy. The next layer of reality's resistance. Missions like NICER on the International Space Station are measuring X-ray pulses from neutron stars to map their shapes and sizes, hoping to constrain the equation of state of nuclear matter. Meanwhile, gravitational wave observatories such as LIGO and VIRGO have already recorded the ripples from colliding neutron stars. The famous event GW170817 in August 2017, where two neutron stars spiraled together, merging into a black hole and forging gold, platinum, and other heavy elements. That single event confirmed what theorists had long suspected. Neutron matter is the crucible of cosmic creation. From a handful of neutral particles comes everything. The most powerful explosions, the most precise clocks, and the most enduring mysteries. It shows that stability and collapse, creation and destruction, are not opposites in physics. They are complementary faces of the same structure, the balance between quantum pressure and gravity's pull. So, how many neutrons can you stack before reality breaks? The answer is both simple and profound, about 10 to the power of 57. The number inside a neutron star. Beyond that, even the laws of physics themselves bend. And yet, this is only the beginning. Because once we know how far we can go before reality shatters, a deeper question follows. Part 2. Why doesn't the atomic nucleus explode? Billions of protons, each one positively charged, each one trying to push every other away, are packed together inside the heart of every atom. By every law of electricity we know, the atomic nucleus should blow itself apart in an instant. And yet, it doesn't. Every solid object you've ever touched, every breath you've ever taken, every planet, every star, all of it exists because those tiny charged particles somehow resist their natural urge to fly apart. Let's start with the raw numbers, because they tell the story more vividly than words. Take 2 protons, separated by just 1 femtometer. That's 1/4,000,000,000th of a meter. At that distance, the repulsive electrical force between them is immense, equal to the weight of roughly 23 kilograms on Earth. Two particles that small, repelling each other with the strength of a bowling ball in your hand. Now imagine not two, but dozens or hundreds of those protons confined within a nucleus only a few femtometers wide. By any ordinary reasoning, that structure should never hold. Gravity, of course, is no help here. It's 10 to the power of 36 times weaker than the electrical repulsion between protons at that scale. That's not a typo. It's a number so large that even the entire mass of the Earth couldn't hold two protons together if all you had was gravity. So what keeps the atomic heart intact? The answer lies in one of the most astonishing discoveries in all of physics. The strong nuclear force. This force is so powerful, so short-ranged, and so unlike anything else, that when it was first theorized in the 1930s, physicists didn't even have a name for it. They simply called it the binding energy, because that was all they could measure. The amount of energy needed to pry protons and neutrons apart. Inside the nucleus, the strong force acts only when particles are extremely close, closer than about 2 femtometers. It doesn't just counter the electrical repulsion, it completely overwhelms it. At short distances, it becomes the most powerful known force in the universe. 100 times stronger than the electromagnetic force. That's why it's called strong. But here's the twist. If you try to pull two protons farther apart, the strong force suddenly fades to almost nothing. It's like an invisible glue that only works when you're right at the surface of contact. Once you pull too far, it lets go entirely. That delicate balance gives rise to every element in the periodic table, from hydrogen to uranium. The story of how we discovered this force is one of the most remarkable in science. It began in 1932, when British physicist James Chadwick discovered the neutron. Until then, no one could explain why heavy atoms were stable when their nuclei were crammed with positively charged protons. Chadwick's discovery of a neutral particle, the neutron, solved part of the puzzle. Neutrons added mass and stability, cushioning the repulsion between protons, but they didn't explain why the nucleus stayed bound. Then came Hideki Yukawa, a young Japanese physicist who, in 1935, proposed that there must exist a new force. A short-range attraction carried by a new kind of particle, which he called a meson. He predicted its mass, its range, and even suggested that it acted as the messenger of the nuclear glue. A decade later, experiments confirmed the existence of such particles. The pions. Exactly where Yukawa had predicted. For this, he became the first Japanese scientist to win the Nobel Prize in physics. The discovery of the strong nuclear force revealed something profound about the structure of matter. Every proton and neutron is made of 3 quarks, held together by the exchange of even smaller particles called gluons, named for exactly what they do. Within each nucleon, gluons bind quarks so tightly that the energy of that binding actually makes up most of the particle's mass. As Einstein showed in his equation, E equals mc. 2. Energy and mass are interchangeable. The mass of a proton is really the trapped energy of its gluons. So when we say the strong force holds the nucleus together, we're not just describing stability. We're describing how matter itself gains its weight. Experiments at particle accelerators like CERN's Large Hadron Collider have tested this theory in exquisite detail. When protons collide at near the speed of light, their inner quarks and gluons briefly separate, creating showers of new particles that vanish again almost instantly. Those flashes confirm that the strong force grows stronger as quarks are pulled apart. A property physicists call confinement. Unlike other forces that weaken with distance, the strong force tightens the farther you stretch it, until it finally snaps, releasing pure energy. That snap is what fuels stars. Inside the cores of stars like our Sun, protons collide at temperatures above 15 million Kelvin. Under such intense heat and pressure, the repulsive Coulomb barrier can be overcome. Protons fuse, releasing energy from the conversion of mass to light. That process, nuclear fusion, is the reason you can see this text, the reason plants grow, and the reason every atom heavier than hydrogen exists at all. But let's return to our original question. Why doesn't the atomic nucleus explode? The truth is, it's constantly trying to. The electric repulsion inside the nucleus is always there, forever pushing outward. The strong nuclear force, acting over those tiny distances, is always pulling inward. The result is a perfect tension, a balance so delicate that if the strong force were just 2% weaker, hydrogen would be the only element that could exist. No oxygen, no carbon, no stars, no life. Even within this balance, there are limits. In heavy elements like uranium or plutonium, the nuclei become so large that the protons are too far apart for the strong force to hold them all together. Electrostatic repulsion starts to win, and the nucleus becomes unstable. That's why such elements are radioactive. They decay, shedding particles and energy until they find a more stable configuration. You can think of it as nature's quiet maintenance system. Whenever matter grows too heavy, too crowded, or too unbalanced, it finds a way to release the excess. Sometimes through gentle decay, sometimes through the blinding brilliance of a supernova. In both cases, the underlying rule is the same. Stability is temporary, maintained by invisible forces that constantly negotiate balance. Modern instruments let us see this balance in action. At Lawrence Berkeley National Laboratory, detectors have observed the brief formation of super-heavy elements, nuclei, with more than 100 protons. That last less than a second before decaying. Meanwhile, space telescopes like JWST and Chandra watch the afterglow of supernovae where new atomic nuclei are born, showing that even cosmic explosions follow the same laws we observe in laboratories. Every flicker of starlight is a message from those invisible forces, reminding us that the strong nuclear bond governs not just the atom, but the cosmos itself. One of the most remarkable demonstrations of the strong force's reach comes from nuclear astrophysics, the study of how elements form inside stars. When massive stars run out of fuel, their cores collapse under gravity, squeezing protons and electrons together to form neutrons, just as we saw in Part 1. The leftover layers then explode outward, scattering the newly forged elements into space. Those same nuclei, held together by the strong force, drift for millions of years until they become part of new planets, oceans, and living beings. The late astrophysicist Carl Sagan once said, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars." He was describing the ultimate expression of the strong nuclear force. The one that not only prevents the atom from exploding, but also lets the universe build itself, layer by layer. In a way, the nucleus is the most disciplined structure in the universe. Every proton inside it wants to escape, but cannot. Every neutron wants to decay, but stays bound. They live in a perpetual truce. repulsion and attraction held in perfect equilibrium by the laws of nature. And it's that balance that gives rise to everything we see, touch, and breathe. So next time you look at anything solid, a stone, a leaf, a planet, remember, beneath its surface, billions of tiny battles are happening every second, and yet the outcome is peace. The strong nuclear force, silent and unseen, keeps every atom whole. But when we step back, when we pull the camera outward from the nucleus to the stars, another struggle begins to emerge. A struggle not inside atoms, but between them. Vast, patient, and almost imperceptible. Because beyond the reach of the strong force lies a gentler one. So weak it can't bind a single proton, yet powerful enough to hold entire galaxies in its arms. Part 3. Is gravity too weak to matter? Or the strongest force in disguise? How can the force that holds galaxies together be so weak that two protons barely notice it? It sounds impossible. At the scale of atoms, gravity seems meaningless. Weaker by more than 1 trillion times than the electrical forces that hold a nucleus together. And yet, on the scale of planets, stars, and entire galaxies, gravity rules everything. Tonight, let's unravel that paradox. How the universe's gentlest whisper becomes its most powerful command. At the atomic scale, the gravitational pull between two protons is almost nothing. Roughly 10 to the power of -34 newtons. That is so faint that if you tried to measure it in a lab, you'd have to wait longer than the age of the universe to detect even a flicker of movement. By comparison, the electric repulsion between those same two protons is about 10 to the power of 36 times stronger. This enormous difference is what physicists call the hierarchy problem. The puzzle of why gravity seems absurdly weaker than the other fundamental forces. And yet, step outside the atomic world, and gravity suddenly becomes unstoppable. Planets orbit stars. Stars cluster into galaxies. Galaxies weave into filaments, stretching across billions of light years. No other force can do that. Electric forces cancel. Positive and negative charges neutralize each other. The strong and weak nuclear forces fade beyond the nucleus. But gravity never cancels. Every atom, every grain of dust, every photon adds its pull to the next. It's cumulative, endless, and always attractive. That's its secret. Gravity may start weak, but it never stops adding up. It doesn't care whether you are an atom or a star. Every bit of mass curves space the same way. Einstein explained this transformation in 1915, when he published the general theory of relativity. He replaced the old Newtonian idea of force with geometry. Space itself bending around mass and energy. Matter tells space how to curve, and space tells matter how to move, as the physicist John Wheeler would later summarize. It's one of the most elegant sentences ever written about nature, and one of the most verified. A century later, we've tested Einstein's equations everywhere we can. NASA's gravity probe B measured the twisting of space-time around Earth, known as frame dragging, with a precision better than 0.1%. The LIGO and Virgo observatories have detected the faint ripples, gravitational waves, from colliding black holes and neutron stars, confirming that space-time itself can vibrate like a drum. And the Event Horizon Telescope, a planet-sized network of radio dishes, has photographed the shadow of a black hole in the galaxy M87, exactly where Einstein's equations predicted it would be. All of this from a force that seems too weak to matter. The paradox runs deeper still. If you shrink to the realm of the quantum, to particles smaller than an atom, gravity begins to misbehave. In quantum physics, every force has a messenger particle. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak. Gravity's messenger, in theory, would be the graviton, a massless particle that hasn't yet been detected. But when we try to describe gravity that way, the math breaks. It predicts infinite energies at tiny distances, which makes no physical sense. This is why, even today, quantum gravity remains one of the most challenging frontiers in physics. Physicists have tried many paths to bridge this gap. Some, like string theory. Imagine that particles are tiny, vibrating loops of energy. They're different modes of vibration, giving rise to all forces, including gravity. Others propose extra dimensions, curled up so tightly we can't see them, where gravity might spread out and lose strength. The Randall-Sundrum model, introduced in the year 2000, even suggests that gravity's apparent weakness could be an illusion, that most of its power is hidden in a fifth dimension beyond our perception. If that's true, then gravity isn't weak at all. It's just leaking into a larger universe. On cosmic scales, its effects are impossible to ignore. Gravity sculpts everything we can observe. In the 1920s, Edwin Hubble used the Mount Wilson Observatory to measure the light from distant galaxies and found that space itself was expanding. That expansion is the counterpoint to gravity's pull, the two most fundamental forces shaping the evolution of the cosmos. Over time, gravity has drawn matter into clusters, galaxies, and stars, while expansion has stretched the fabric of the universe apart. Every structure we see in the sky, every star and planet, exists because gravity won the local battle, even while losing the global one. To understand just how universal gravity is, consider this. A single teaspoon of neutron star matter weighs billions of tons, because gravity compressed the same number of particles into a space barely the width of a city. That same force, scaled up, can bend the path of light itself. Something confirmed during the 1919 solar eclipse, when Arthur Eddington measured starlight curving around the sunday. That observation made Einstein world-famous overnight. Gravity's influence has no limit in range. It reaches from your body to the moon, from the moon to the sun, from the sun to the edge of the observable universe. Unlike other forces that fade to zero or cancel, gravity follows an inverse square law. Double the distance, and the pull weakens by 4. But it never truly vanishes. This is why galaxies can still feel each other's tug across millions of light years. What's more, gravity interacts with everything that has energy, not just mass. Light itself, though weightless, bends in gravitational fields because energy curves space-time just as mass does. This leads to phenomena like gravitational lensing, where massive clusters of galaxies bend the light from even more distant galaxies behind them. Images from NASA's Hubble Space Telescope and the James Webb Space Telescope have captured these distortions in exquisite detail. Arcs of light stretched and mirrored by invisible mass. It's one of the most beautiful confirmations of general relativity, gravity, turning the cosmos into its own natural telescope. But there's still a question that keeps physicists awake. Why does gravity seem to have no opposite? Electricity comes in plus and minus. The strong and weak forces can both bind and decay, but gravity is always attractive. It only pulls. That universality may be the reason it dominates the large-scale structure of the cosmos. The Planck satellite and Euclid mission have mapped the cosmic web. Enormous filaments of galaxies and dark matter stretching across billions of light-years. These structures exist because gravity slowly pulled matter together from the almost uniform early universe. Yet about 70% of the cosmos now appears to be something even more mysterious. Dark energy, a kind of negative pressure that pushes space apart. NASA's Nancy Grace Roman Space Telescope, launching soon, aims to study this delicate balance between gravity's pull and dark energy's push. The result may reveal whether gravity itself changes across cosmic time. A hint that the universe's strongest force might still be evolving. And there's another possibility. Some theories suggest that gravity could be emergent. Not fundamental at all, but the collective effect of countless microscopic interactions, like temperature, emerging from molecular motion. If so, gravity might not be a basic ingredient of nature, but a byproduct of information, energy, and entropy, woven into spacetime. The physicist Eric Verlinde once described it this way: gravity is the tendency of systems to maximize entropy. It's an elegant, if still unproven, idea. One that hints at gravity's hidden link to the quantum world. From the smallest proton to the largest supercluster, gravity connects everything. It is the universe's quiet background hum, imperceptible in the laboratory, unstoppable in the sky. It starts as a whisper, becomes a rhythm, and ends as a roar that shapes galaxies, stars, and time itself. So yes, gravity is weak, almost laughably so, when measured between atoms, but it's also the most patient and most universal force we know. It never cancels, never tires, and never forgets. Given enough mass and enough time, it always wins. And in that quiet, unhurried victory lies the key to everything that follows. For when gravity gathers enough strength to crush the heart of a star, it begins to forge the heavy elements: gold, uranium, and all that sparkle inside the periodic table. But nature has a limit even here. A point where those massive atoms, born from fire, begin to tremble under their own weight. Part 4. Why do heavy elements teeter on the edge of destruction? Why does nature allow atoms so large that they nearly fall apart? It's one of the most delicate questions in physics, because the answer reveals how even matter itself lives on a razor's edge between creation and decay. Every heavy element we know, from gold to uranium, exists only because opposing forces in the atomic nucleus, attraction and repulsion, are locked in a fragile standoff. If that balance shifts even slightly, the atom collapses or explodes. Inside any atom's core, hundreds of protons are squeezed together, each carrying the same positive electric charge. They should repel each other violently, and they do. But the strong nuclear force pulls them inward, overpowering that repulsion at close range. This force acts only across distances of a few femtometers, about the width of a single proton, and within that range it's the most powerful binding known in the universe. It's what glues the atomic heart together, but as nuclei grow larger, this invisible glue begins to fail. The strong force saturates. It doesn't keep growing with the number of particles. Protons feel the attraction only from their nearest neighbors, while the electrical repulsion what physicists call the Coulomb force, increases with every additional proton. In simple terms, the more protons you pack in, the faster the tension rises. That's why light elements like carbon and oxygen are rock stable, but heavy ones like uranium exist on borrowed time. At a certain size, around 82 protons, the electrostatic push becomes so strong that no number of neutrons can stabilize the nucleus for long. Neutrons help by adding mass and acting as spacers between protons, softening their repulsion, but even they can't hold the structure forever. Beyond this threshold, nature resorts to decay. Take uranium-238, one of the heaviest naturally occurring elements. Its nucleus contains 92 protons and 146 neutrons, bound in an uneasy compromise. Every second, about 2.5 billion atoms of uranium in a small sample transform, quietly emitting alpha particles, which are helium nuclei, as they decay toward more stable forms. Each transformation releases energy, not because anything is burning, but because the nucleus is sliding toward a configuration of lower internal stress. This slow disintegration, called radioactivity, was discovered in 1896 by Henri Becquerel in France. He noticed that photographic plates stored near uranium salts became fogged, as though they'd been exposed to light. Later, Marie and Pierre Curie identified new radioactive elements, polonium and radium, revealing that atoms themselves could change identities. It was a shocking idea at the time. Until then, atoms were believed to be the unbreakable foundations of nature. As it turns out, the reason they break is deeply mathematical. If the number of protons grows faster than the number of neutrons, the nucleus becomes imbalanced. Protons repel one another, while neutrons, which interact only through the strong force, add stability. For small atoms, a 1-to-1 ratio works. For medium ones, a few extra neutrons are needed, but for the heaviest nuclei, the ratio climbs. Uranium needs almost 1.6 neutrons for every proton just to hold together for a geological blink. Even then, it's a temporary victory. Eventually, the strong force can no longer compensate for the ever-growing electric push. The nucleus releases energy by splitting apart, shedding particles until it reaches a more comfortable balance. That's what we see in nuclear fission. The process first observed in 1938 by Otto Hahn and Lise Meitner. They found that when uranium absorbs a neutron, it can elongate and divide into two smaller nuclei, releasing vast amounts of energy in the process. The energy comes directly from Einstein's famous relation between mass and energy. A tiny loss of mass inside the atom turns into a tremendous burst of heat and light. The same mechanism powers both nuclear reactors and atomic bombs. In reactors, the process is controlled, allowing the slow release of energy to generate electricity. In weapons, it's uncontrolled, releasing that energy in microseconds. But whether in a lab or a star, the principle is the same. Matter seeks balance, and in doing so, it radiates the excess energy it no longer needs. It's easy to forget that radioactivity is not rare. It's everywhere. The potassium in your muscles, the carbon in your bones, the granite beneath your feet, all contain tiny traces of unstable isotopes. Every second, a few thousand atoms inside your body decay, releasing harmless particles that pass unnoticed through dotobes. That quiet decay has been happening since the dawn of time. On a planetary scale, radioactivity is one of the most important heat sources in the universe. The Earth's interior stays molten not just from its ancient formation, but because isotopes like uranium-238, thorium-232, and potassium-40 continue to release heat as they decay. Without that warmth, plate tectonics would stop, volcanoes would die out, and the magnetic field protecting our planet from cosmic radiation would fade. So, even instability sustains life. Astronomers have discovered that heavy elements, like uranium and gold, were not born inside ordinary stars at all. They require conditions so extreme that only cataclysmic events can forge them. In 2017, the gravitational wave event GW170817, recorded by LIGO and VIRGO, confirmed that when two neutron stars collide, their cores eject enormous amounts of neutron-rich matter. In seconds, that debris cools and condenses into the heaviest elements known. Spectroscopic data from NASA and ESA's telescopes showed clear signatures of freshly made gold, platinum, and uranium. Billions of tons of them, drifting into space. The very atoms that now lie inside our jewelry, our electronics, and even our blood, were born in those stellar collisions. Yet even those precious atoms are not forever. Over cosmic timescales, they too will decay. Each heavy nucleus transforming into lighter elements, step by step, over billions of years. It's a reminder that the universe never stops recycling itself. As NASA's astrophysicist Jennifer Johnson put it, every atom heavier than iron tells a story written in the death of stars. When we measure the half-life of uranium-238, about 4.5 billion years, we realize it's almost exactly the age of Earth itself. That's not a coincidence. It means the uranium we find today was forged just before our planet formed. What remains is the last whisper of that ancient process, still echoing through the rocks beneath our feet. Even in laboratories today, scientists continue to push the boundaries of nuclear stability. At the Joint Institute for Nuclear Research in Russia and Lawrence Livermore National Laboratory in the United States, researchers have created super-heavy elements like oganesson element 118, which exists for less than 1,000th of a second before vanishing. These fleeting creations hint that there might be an island of stability, a region of yet unknown elements that last longer than any predicted so far. If found, such elements could reveal new physics at the intersection of quantum mechanics and nuclear structure. It's extraordinary to think that the universe allows such a precarious balancing act, that matter can hover between cohesion and collapse for billions of years. Even the heaviest atoms owe their existence to the same principles that govern stars and galaxies, competing forces seeking equilibrium. The strong nuclear force tries to hold everything together. The Coulomb force insists on pushing it apart. The result is tension. And from that tension comes energy, light, and motion. In that sense, instability is not a flaw but a feature. Without decay, there would be no energy flow, no element synthesis, no dynamic universe. Everything we see is part of that ongoing adjustment. The cosmos forever tuning itself toward balance, never quite reaching it. And so, when we ask why heavy elements teeter on the edge of destruction, the answer is simple and astonishing. Because that edge is exactly where the universe creates. Too stable and nothing changes. Too unstable and nothing lasts. Between them lies a narrow band. The fragile middle ground where stars burn, planets form, and matter remembers to hold itself. just barely, together. But even that balance cannot last forever. For there comes a moment when the gentle rules of atoms give way to something far more powerful. When gravity steps in and begins to compress matter beyond what any nucleus can bear. It is here that quantum law itself must decide whether reality can still resist collapse. Part 5. Can quantum rules stop you from building a neutron mountain? What if the laws of quantum mechanics themselves refuse to let reality grow any denser? What if, no matter how much matter you try to pile up, an invisible resistance rises? Not from heat, not from explosion, but from the quiet order of nature's smallest rules. This is the strange boundary discovered at the meeting point of nuclear physics and quantum mechanics, where particles stop obeying human intuition, and even gravity must wait its turn. Neutrons, like protons and electrons, belong to a special family of particles called fermions. And fermions live under one unbreakable rule, the Pauli exclusion principle. Proposed by physicist Wolfgang Pauli in 1925, it states that no two identical fermions can occupy the same quantum state at the same time. In simple terms, nature doesn't allow particles like neutrons to share the same space in the same energy condition. It's as if the universe quietly enforces a rule of personal space at the smallest possible scale. This rule explains why matter has structure at all. Electrons don't collapse into the nucleus because they must fill different orbits, each with its own distinct energy level. Neutrons and protons within the nucleus also organize themselves in shells, just like electrons in atoms. Each particle finds the lowest energy seat available, and when those are full, the next ones must go higher. That silent stacking creates pressure. A pressure not from temperature or collisions, but from quantum order itself. Now imagine what happens when you try to build a mountain of neutrons, compacting matter denser and denser. At first, the neutrons fit comfortably, but as you add more, they begin to resist. Because each must occupy a unique energy state, they start filling higher momentum levels, which means their average energy increases. This rising energy, known as degeneracy pressure, acts like an invisible barrier that prevents matter from compressing indefinitely. This concept isn't just theoretical. It's the same principle that supports white dwarfs, the remnants of medium-sized stars like our Sunday. When such stars exhaust their nuclear fuel, they collapse inward under gravity, squeezing electrons together. But the electron degeneracy pressure pushes back, holding the star from further collapse. That balance creates a white dwarf roughly the size of Earth, but with the mass of the Sun. A density of about 10 to the power of 9 kilograms per cubic meter. It's quantum physics that prevents it from becoming smaller. However, when even more mass is added, typically more than 1.4 solar masses, known as the Chandrasekhar limit, electron pressure can no longer hold back gravity. The electrons combine with protons, forming neutrons and releasing neutrinos. At that moment, the star transforms into something far stranger, a neutron star. Inside a neutron star, the same exclusion principle takes over again. But this time, it's neutrons providing the degeneracy pressure. Each neutron occupies its own quantum state, resisting compression not through heat, but through the very geometry of quantum space. As the density climbs beyond 10 to the power of 17 kilograms per cubic meter, neutrons are packed so tightly that a teaspoon of this matter would weigh billions of tons. Yet even then, collapse stops. Not because gravity gives up, but because quantum mechanics says no further. This is one of the most extraordinary facts in nature, that the same principle defining how electrons fill atoms also defines the fate of stars. When Pauli first proposed his exclusion rule, he couldn't have known it would explain the behavior of celestial bodies millions of times heavier than Earth. In 1930, the young Indian astrophysicist Subramanian Chandrasekhar applied quantum mechanics to stellar structure, showing how degeneracy pressure governs the destiny of dying stars. For this insight, he later received the Nobel Prize in Physics, 1983, and his work remains one of the most elegant examples of how microscopic laws shape cosmic architecture. Let's visualize what actually happens inside such dense matter. At lower densities, neutrons behave like ordinary particles, bouncing around with moderate speeds. But as they're squeezed closer, the quantum rule forces them into higher energy states, meaning their momentum and velocity skyrocket. This increase in energy creates a counter-pressure that grows rapidly with density. Even at absolute zero, where classical pressure vanishes, degeneracy pressure persists. It's a purely quantum effect. The universe's built-in safeguard against infinite collapse. However, this quantum safeguard has limits. The neutron degeneracy pressure can only hold back so much gravity. Once the mass exceeds about 2.2 to 2.9 solar masses, the Tolman-Oppenheimer-Volkoff limit, calculated in 1939, gravity wins. At that point, the neutrons are forced into the same quantum states, something that nature forbids. The only possible outcome is that space itself collapses and a black hole forms. That's not destruction in the usual sense. It's reality rearranging itself. It's fascinating to realize that this invisible resistance, this quiet quantum rule, is what defines the architecture of our universe. Without it, stars would collapse instantly after burning their fuel. Galaxies would be filled only with black holes. Planets, atoms, and chemistry would never have the chance to exist. Everything solid, stable, or structured depends on the exclusion principle's invisible hand. Physicists often call this phenomenon quantum degeneracy pressure, but the word pressure can be misleading. It's not molecules pushing against each other. It's a mathematical expression of how the allowed energy states are distributed. When the lowest states are filled, any additional particle must jump to a higher level, adding to the total energy. That rising energy behaves exactly like a pressure, holding matter apart. As Richard Feynman once said, Pauli exclusion is not a recommendation, it's a commandment. It's one of the few laws the universe absolutely refuses to bend. Evidence for this rule isn't limited to theoretical models. In 2017, NASA's NICER instrument aboard the International Space Station measured the size and mass of several neutron stars by analyzing their X-ray emissions. The data revealed that all known neutron stars, regardless of their composition, fall within a narrow range of radii, about 11 to 14 kilometers. That uniformity confirms the presence of a universal internal pressure. Exactly what quantum mechanics predicts. It's the same invisible quantum wall we're talking about, written across the sky in X-rays. Meanwhile, at the European CERN accelerator, scientists collide atomic nuclei at near-light speeds to briefly recreate conditions of extreme density. In those collisions, protons and neutrons melt into a fluid of quarks and gluons, what physicists call quark-gluon plasma, similar to the matter that existed microseconds after the Big Bang. By studying how this plasma expands, They test the limits of degeneracy and confinement, exploring whether quantum pressure could hold even this chaotic state together. It's the same question, reframed at the smallest possible scale. How far can reality be squeezed before it stops being what we know? Even the behavior of white dwarfs and neutron stars, confirmed by space telescopes like Chandra and JWST, supports the same principle. The light we see from these compact stars tells us their temperatures, densities, and ages. And every measurement agrees with quantum predictions to astonishing precision. The laws Pauli wrote nearly a century ago still shape the night sky. It's strange, isn't it, that the same rule preventing two electrons from sharing an atomic orbital also prevents the collapse of dying stars. That the pattern of quantum shells inside your body's atoms mirrors the invisible structure of objects 1,000 trillion times heavier. Across scales unimaginable, nature reuses the same logic. Space must be shared fairly, even among particles that cannot think or choose. This balance between gravity's relentless pull and quantum mechanics' quiet resistance defines the boundary between existence and oblivion. It's the first true wall that nature builds, not of stone or energy, but of principle. The wall says, no two fermions may ever become one. And from that single restriction arises everything that holds shape in the cosmos. From the atoms in your hand to the stars that burn in distant galaxies. So yes, quantum rules can stop you from building a neutron mountain. They can halt the collapse of a star, resist the compression of matter, and preserve the quiet architecture of space within space. It isn't the explosion that defines the boundary, but the silence. The soft hum of quantum order pushing back against gravity's pull. But there is still one question waiting at the very edge of that invisible wall. If quantum pressure can hold the universe together, what happens when gravity grows strong enough to crush even the quantum itself? What does the universe create when every smaller law surrenders and space-time takes command? Part 6. When gravity takes over, the birth of the neutron star. What happens when gravity grows strong enough to replace the atomic forces themselves? When the gentle push and pull inside every atom can no longer resist the weight above it? When the rules of the small surrender to the laws of the immense? A star crosses a point of no return. At first, it seems impossible. How could a force so feeble, so hopelessly weak between atoms, ever become strong enough to crush a star? Yet, that is precisely what gravity does. It waits, it accumulates, it turns patience into power. Imagine the heart of a massive star near the end of its life. After millions of years of burning, it has fused hydrogen into helium, helium into carbon, carbon into oxygen, and so on, until it reaches iron. But iron is the dead end of fusion. When the core becomes mostly iron, the process that once released energy begins to consume it, and as outward pressure fades, gravity senses its moment. It begins to collapse the star inward. The core, once the size of a planet, shrinks within seconds to something barely 20 kilometers across. This is the beginning of a neutron star. Inside that collapsing core, the density climbs beyond imagination around 10-17 kilograms per cubic meter. That's roughly the mass of a mountain squeezed into a single teaspoon of matter. At these densities, electrons are crushed into protons, forming neutrons and releasing neutrinos that stream outward in torrents. The strong nuclear force, which once held atomic nuclei together, can no longer act across such immense pressures. Gravity becomes the architect now. In A, first course in general relativity, Bernard Schutz once described this transition point, where gravity traps neutrons permanently, as the threshold between nuclear physics and space-time physics. If matter reaches nuclear density, he calculated, an object needs to be at least about 0.02 times the mass of our Sun for gravity to hold neutrons together without them decaying. At that scale, the familiar atomic world vanishes. The protons, neutrons, and electrons we know melt into one continuous sea of degenerate matter. The result is something neither solid, liquid, nor gas, but a new state of existence altogether. NASA describes neutron stars as the smallest and densest known objects in the universe that are not black holes. A typical neutron star contains more mass than our Sun, compressed into a sphere only about 20 kilometers wide. Its surface gravity is about 200 billion times stronger than Earth's. If you could, stand on its surface, though you never could. One small step would release more energy than the detonation of every nuclear bomb on our planet combined. At such densities, even light struggles to escape cleanly. The escape velocity from the surface of a neutron star is about half the speed of light, roughly 150,000 kilometers per second. Einstein's general relativity must now take the lead. Newton's laws are no longer enough. The space-time around this star curves so deeply that geometry itself becomes part of the story. The idea that gravity could crush matter into neutrons was first proposed in the 1930s, shortly after James Chadwick discovered the neutron. Physicists Lev Landau and J. Robert Oppenheimer each speculated that when a star's core becomes too massive for electron pressure to support it, the collapse would continue until protons and electrons fused into neutrons. This theory seemed abstract for decades, until the 1960s, when astronomers detected radio pulses coming from distant points in the sky. They called them pulsars. We now know each pulse came from a spinning neutron star, a remnant of a star's collapse, rotating with incredible precision, shining like a lighthouse through the cosmic dark. Inside these stars, gravity and quantum mechanics achieve a delicate truce. Quantum degeneracy pressure, the same principle that once stopped white dwarfs from collapsing, now operates on neutrons instead of electrons. Each neutron resists being squeezed into the same state as its neighbor, creating a pressure that holds the star against further collapse. But the scale of that balance is unimaginable. A neutron star's internal pressure equals roughly 34 pascals, 100 trillion times the pressure inside Earth's core. It is a silent battle between quantum law and the weight of the cosmos itself. ESA's XMM Newton and NASA's NICA missions have observed these compact stars in exquisite detail. NICA, mounted on the International Space Station, measures X-ray emissions from neutron stars to map their surfaces with microsecond precision. From these signals, we've learned that some neutron stars spin hundreds of times per second, yet remain perfectly stable, held together by the same geometry that once seemed destined to destroy them. The elegance of it all is quiet, but staggering. Here is matter pushed beyond every boundary we know, where gravity curves space so deeply that it almost touches the threshold of a black hole, and yet quantum rules still whisper, enough. It is at this fragile intersection that nature writes her most extreme equations, the point where the collapse of a dying star becomes the birth of a new kind of object. Not destroyed, but transformed. Every neutron star we observe today tells that same story, a balance between the hunger of gravity and the resistance of quantum order. Each one is a fossilized heartbeat from a once-living star, proof that the universe keeps nothing forever, but never truly loses anything either. And so, when we talk about the birth of a neutron star, what we really mean is this: that the laws of nature, when pushed to their breaking point, learn to rewrite themselves. From that rewriting, the cosmos continues. Because once gravity has taken over, once it has replaced the atomic forces themselves, nothing remains the same. But even this new kind of stability cannot last forever. For if gravity can shape a neutron star, what happens when it gathers enough mass to crush even this final form of matter? Part 7. How heavy must a neutron star be to exist? How much mass does it take for space-time itself to hold neutrons captive? At what point does gravity become so intense that even the quantum resistance of matter, the silent push of the Pauli exclusion principle, surrenders and turns into a new state of being? This is the threshold that separates an ordinary collection of particles from one of the strangest and most extreme objects in the universe, the neutron star. Every neutron star begins the same way, in the heart of a collapsing massive star. When a star several times heavier than the Sun exhausts its nuclear fuel, the outward pressure from fusion fades, and gravity wins. The outer layers crash inward, hitting the dense core at speeds reaching thousands of kilometers per second. Protons and electrons are crushed together to form neutrons, and a burst of neutrinos carries away the excess energy. What remains is a core made almost entirely of neutrons, an object so dense that a teaspoon of it would weigh billions of tons. But here's the fascinating question. How much mass does that remnant need before gravity can hold it together permanently? If there's too little mass, the neutrons will drift apart. Too much, and they'll collapse into a black hole. There must be a sweet spot, a balance point, where nuclear and gravitational forces meet perfectly. We can estimate that balance with surprising accuracy using only simple physics. Start with nuclear binding energy, the energy that holds a nucleus together. For ordinary nuclei, this energy is about 8 mega-electron volts per nucleon, the amount needed to tear a neutron or proton free from the rest. Now compare that to the gravitational binding energy, the energy required to pull all the matter in a sphere apart against its own gravity. When these two values become roughly equal, gravity becomes strong enough to prevent neutrons from escaping. That happens at around 0.04 times the mass of the Sun. A rough Newtonian estimate. It's astonishing that such a simple calculation, balancing the nuclear and gravitational terms, already points to the correct order of magnitude. But the real universe isn't Newtonian. When matter becomes this dense, gravity no longer behaves as a mere force. It becomes geometry. Space itself curves, and time slows down. To model that, physicists use the Tolman-Oppenheimer-Volkoff equations, derived in 1939, which describe how pressure, density, and space-time curvature interact inside an ultra-dense star. Those equations refine the minimum stable mass to about 0.1 solar masses, or roughly 2 times 10 to the 29 kilograms. That's the smallest amount of mass the universe needs to trap neutrons forever. Anything lighter can't hold itself together. The neutrons decay back into protons and electrons within minutes. Anything heavier will compress, until the quantum pressure of neutrons halts collapse, forming a true neutron star. It's an elegant bridge between two theories that rarely meet: Newton's simple gravity and Einstein's curved spacetime. It's remarkable how the predictions align with reality. Astronomers have measured neutron stars across our galaxy, and none are lighter than about 1.1 solar masses. 10 times above the theoretical minimum, but still in the same cosmic neighborhood. That's confirmation that even simplified physics can approximate nature's most extreme behavior. As the astrophysicist Freeman Dyson once said, "A good theory predicts something we could not have imagined and then finds it in nature." Here, the prediction and observation meet almost perfectly. To understand how such a star holds itself together, picture the competing pressures inside. At the center, neutron degeneracy pressure, the quantum push that keeps neutrons from occupying the same state, tries to expand the star. Gravity, on the other hand, presses inward with unimaginable strength. At equilibrium, these two effects balance so precisely that if you added just 1% more mass, the entire star could collapse into a black hole. That's why neutron stars have such a narrow range of masses, between about 1.1 and 2.3 solar masses. Modern observations confirm these limits. In 2010, NASA's Rossi X-ray Timing Explorer detected millisecond pulsars, rapidly spinning neutron stars, whose timing data revealed masses near 2 solar masses. That measurement set the upper bound for how much matter neutron degeneracy can support. Below that, general relativity ensures that spacetime curvature strengthens as density increases, tightening the structure even further. It's gravity itself that sculpts the final form. Einstein's equations predict that the gravitational potential inside such an object is enormous. Near its surface, the escape velocity reaches about 0.5 times the speed of light. That means a photon emitted from its surface loses half its energy, simply climbing out of the gravitational well. A phenomenon known as gravitational redshift. NASA's NICER mission, orbiting aboard the International Space Station, has measured this effect precisely by observing the thermal X-rays from pulsars. Those observations confirm what theory had long suggested. Neutron stars are not only massive and small, but also deeply relativistic. The curvature around them is so strong that time itself runs slower near their surface than it does here on Earth. If you could hover safely above one, a single second for you would correspond to several seconds for a distant observer. This isn't speculation. It's a direct prediction of general relativity, confirmed by timing the pulses from spinning neutron stars thousands of light years away. But how do we know how heavy they truly are? Astronomers rely on binary systems, pairs of stars orbiting one another. When one star becomes a neutron star, its gravity tugs on its companion, and the orbital motion reveals its mass. In some systems, the neutron star emits regular pulses, allowing incredibly precise measurements. One such object, PSRJ 348 plus 0432, was found to weigh 2.01 solar masses, pushing the limit of stability predicted by theory. Another, PSR J740 plus 6,620, measured by NICER in 2021, came in at 2.08 solar masses, perhaps the heaviest stable neutron star ever found. Beyond that limit, no known equation of state, no arrangement of nuclear matter, can resist gravity's final pull. Even the surface gravity of a neutron star defies comprehension. It's about 10 to the power of 11 times stronger than Earth's. Drop an object from just 1 meter above the surface, and it would strike at speeds approaching half the speed of light. No solid material could survive that fall. Not steel, not diamond, not even atomic nuclei. Only the balance of quantum mechanics and relativity keeps the star from disappearing altogether. Inside, matter exists in forms we can't yet reproduce on Earth. At the core, pressures exceed 10 to the power of 35 pascals, forcing neutrons into close contact until their internal quarks begin to overlap. Some models suggest that at those densities, the neutrons dissolve into a sea of deconfined quarks, forming what scientists call quark matter or strange matter. Others predict layers of exotic phases, superfluids, superconductors, or even crystalline lattices of neutrons, arranged in nuclear pasta shapes, spaghetti-like filaments, and lasagna-like sheets. Each phase follows the same logic: the battle between confinement and gravity. This combination of precision and mystery is what makes neutron stars so captivating. They are the most accurate clocks in the universe, some rotating hundreds of times per second with unwavering regularity. Yet, they also conceal physics we still cannot fully describe. Every observation brings us closer to uniting the classical and quantum worlds. The dream Einstein never achieved. And remarkably, much of this behavior can be approximated by simple Newtonian reasoning, just balancing gravitational and nuclear energies. It shows how deeply connected our everyday physics is to the most extreme environments imaginable. If you think about it, these calculations span 55 orders of magnitude, from the size of atomic nuclei to stars several kilometers across. And yet, the same equations work. That unity across scale is one of the most beautiful aspects of physics. That a concept developed for laboratory nuclei can predict the fate of entire stars. Even NASA's Chandra X-ray Observatory and ESA's XMM Newton have confirmed this balance through spectral measurements, showing that theory and observation walk hand in hand. The story of the neutron, star's minimum mass, is a reminder of how physics often begins with simplicity and ends in awe. A handful of equations from Newton and Einstein, written almost a century apart, still guide us to understand an object whose density defies imagination. Between them lies the perfect harmony of old and new. One describing gravity's pull, the other describing the structure of matter itself. Together, they predict the exact point where space stops being empty and becomes a force strong enough to hold neutrons forever. So how heavy must a neutron star be to exist? At least a tenth of our sun's mass. But in truth, it is usually much more. Enough for gravity to bend space-time so deeply that even the strongest quantum resistance begins to yield. Enough to turn collapsing atoms into one seamless ocean of neutrons. A single, unbroken quantum body, held together not by heat, not by fusion, but by the shape of space itself. Here, gravity no longer competes. It commands. Matter becomes geometry. And yet, another question quietly forms in the background. One that waits beyond even this perfect balance. What happens when the mass grows heavier still? When the inward pull stretches space-time to its breaking point, and even the pressure of neutrons, the last defense of matter, can no longer push back. Part 8. What happens when neutrons collapse beyond their limit. What happens when even the deepest laws of quantum mechanics can no longer hold the universe together? When the quiet pressure of neutrons, the final barrier against gravity, reaches its breaking point, that moment marks one of nature's most extraordinary transitions, when matter stops being matter and space itself begins to fall. Up to a certain mass, the dense core of a dead star can resist collapse. Quantum mechanics supplies the push. A silent, invisible pressure arising from the Pauli exclusion principle, which forbids neutrons from sharing the same quantum state. But when a star's mass grows too great, that quantum resistance weakens, and gravity takes control. This critical threshold is known as the Tolman-Oppenheimer-Volkoff limit, or TOV limit. Calculated in 1939 by physicists Robert Oppenheimer, George Volkoff, and Richard Tolman, it defines the upper mass a neutron star can have before collapsing under its own gravity. That limit lies somewhere between 2.2 and 2.9 times the mass of the Sun, depending on the exact physics of nuclear matter inside the core. Beyond this boundary, no known force, not the strong nuclear interaction, not quantum degeneracy pressure, can withstand the inward pull of gravity. Once the star crosses that mass, collapse becomes inevitable. To understand what that collapse really means, we must picture what's happening inside. A neutron star is already astonishingly dense, about 10 to the power of 17 kilograms per cubic meter. But as gravity overcomes quantum pressure, the star's radius begins to shrink, falling inward faster and faster. The neutrons themselves are squeezed beyond recognition. Their internal quarks, normally confined by the strong force, are forced so close together that they lose their individual identities. Matter as we know it ceases to exist. At this point, space-time itself begins to warp. According to Einstein's general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. When the curvature becomes extreme enough, all paths, even those of light, curve inward. The collapsing matter passes a critical boundary known as the event horizon. Once it crosses that invisible surface, nothing can escape. A black hole is born. The transition from neutron star to black hole is not an explosion. It's a quiet implosion. All the matter that once had structure, temperature, and pressure is compacted into a region smaller than any instrument can measure. Outside, the gravitational field continues to act as though the entire mass is still there. Only now, it's contained within an infinitesimal point where density and curvature become infinite. Physicists call this the singularity. It's not a place in space, but rather a point where our equations lose meaning. In Oppenheimer's original 1939 paper, he described this collapse as an unstoppable process, writing that the star continues to contract until the light from its surface can no longer escape. At the time, even Einstein doubted such objects could exist, but over the next decades, evidence began to mount. In the 1960s, radio astronomers discovered quasars, extremely bright, compact sources of radiation at the centers of distant galaxies. Their energy output could only be explained by matter falling into massive black holes. Then, in 1971, the first stellar mass black hole candidate, Cygnus X1, was identified through its X-ray emissions. NASA's Chandra X-ray Observatory later confirmed that its invisible companion had a mass of about 15 solar masses, well beyond the TOV limit. This was the first direct evidence that neutron degeneracy pressure had indeed failed. and gravity had won. Today, observatories across the world continue to study these cosmic remnants. The Event Horizon Telescope captured the first image of a black hole's shadow in 2019, located in the galaxy M87, about 55 million light-years away. That image wasn't a photograph of the singularity itself. Nothing can capture that. But of the light orbiting just outside the event horizon, distorted by extreme gravity. It matched Einstein's predictions precisely. As NASA put it, we've seen the unseeable. So what truly happens inside the event horizon, beyond the point where neutrons collapse? No one knows for certain. According to general relativity, the collapse continues until density becomes infinite. But quantum physics suggests that something else must happen. Perhaps space-time itself becomes granular, or a new form of matter emerges. Theorists like Stephen Hawking, Roger Penrose, and John Wheeler all explored this mystery, trying to unite gravity and quantum mechanics into one framework. Hawking showed that black holes aren't perfectly black. Quantum effects near the event horizon allow them to emit faint radiation, now known as Hawking radiation, meaning they can slowly evaporate over unimaginable timescales. For a black hole of stellar mass, that would take roughly 10 to the power of 67 years. In comparison, the universe today is only 13.8 billion years old. Less than a blink in that cosmic lifetime. It's one of the most subtle consequences of quantum physics. Even when gravity appears absolute, the quantum still whispers through. This confrontation between quantum pressure and gravitational collapse is one of the deepest tensions in modern science. Every black hole represents a failure of our current theories to describe the universe under its most extreme conditions. We know the equations on both sides. General relativity for the large, quantum mechanics for the small. But at the center of a black hole, they contradict each other. Something must reconcile them. Many approaches have been proposed. String theory suggests that particles are not points, but vibrating loops, smoothing out the infinities of singularities. Loop quantum gravity, developed by physicists like Carlo Rovelli, proposes that space-time itself is made of discrete atoms of geometry, preventing it from collapsing to a true point. Neither idea has yet been proven, but both suggest that at the heart of a black hole, reality may transform into something fundamentally new. Meanwhile, astronomers continue to observe the birthplaces of these objects in real time. The gravitational wave observatories LIGO and Virgo have detected collisions between massive neutron stars, where the final merged object collapses into a black hole within seconds. The most famous of these, GW 170817, observed in 2017, produced both gravitational waves and light, allowing NASA's Fermi and ESA's Integral telescopes to detect a gamma-ray burst from the same source. It was the first multi-messenger observation in human history, confirming that black holes are not theoretical abstractions. They are real, and they shape the evolution of galaxies. Inside that final collapse, the geometry of space-time changes so quickly that even time itself stops being well-defined. From an outside observer's perspective, the surface of the collapsing star seems to freeze at the event horizon, never quite disappearing. But to the matter falling inward, the journey continues. Not into a void, but into a region where every known coordinate breaks down. Einstein's equations can describe that collapse mathematically, but they cannot tell us what it means physically. One of the most haunting aspects of this process is that information. the detailed state of the particles that formed the black hole, appears to vanish. This leads to the black hole information paradox, another clash between quantum physics, which forbids information loss, and relativity, which predicts it. Hawking himself wrestled with this paradox for decades, suggesting that information might be encoded in subtle fluctuations of the event horizon. Modern theories propose that the answer may lie in quantum entanglement, linking the interior and exterior of the black hole in ways we don't yet fully understand. All of this, the equations, the paradoxes, the observations, stems from a simple question. What happens when the last barrier of matter collapses, when neutrons, the strongest building blocks of ordinary matter, yield to gravity's relentless pull? The answer is both terrifying and beautiful. Space-time caves in, forming a region where the familiar rules of physics no longer apply. It's relativity's final triumph over quantum resistance. And yet, the story doesn't end there. Because while black holes seem like the universe's full stop, they are also its most mysterious laboratories, where destruction and discovery share the same event horizon. Each one is a testing ground for the deepest questions in physics, a bridge between the known and the unknown. Every photon bent around a black hole, every ripple of space-time from their collisions, brings us closer to understanding how the universe truly works. As NASA describes it, black holes are where the boundaries of code, knowledge meet the edges of imagination. They are the places where gravity becomes pure geometry, and where the universe hides its greatest secrets. In their silence lies the next step of our exploration, a step that moves beyond matter, beyond collapse, into the very shape of space and time itself. But before we vanish completely into that silence, let's turn our gaze to the edge, to the strange survivors just shy of the abyss, where matter still resists collapse by spinning faster and faster to keep its balance. If neutron stars mark the victory of quantum pressure, and black holes mark gravity's final triumph, then between them lies a realm where motion itself becomes the last defense against collapse. Part 9. Why do neutron stars spin and flash like cosmic clocks? How can a dead star spin 1,000 times per second without tearing itself apart? How can something the size of a city rotate faster than any machine ever built, beam light across space with atomic precision, and never slow, even after millions of years? These are the questions that led astronomers to one of the most astonishing discoveries of the 20th century. The pulsar, a neutron star that spins and flashes like a cosmic clock. To understand how a neutron star spins so fast, we have to go back to the moment of its birth. When a massive star dies, it collapses under its own gravity. The outer layers fall inward, compressing the core to nuclear densities. As the radius shrinks from millions of kilometers to barely 10 or 15, one physical law becomes inescapable: the conservation of angular momentum. Just as a figure skater spins faster when pulling in her arms, a collapsing star spins faster as it contracts. Imagine a star the size of our Sun, rotating once every few weeks. When it collapses into a sphere only 13 kilometers wide, its rotation speeds up enormously, turning once every 0.001 seconds. That's roughly 1,000 rotations per second, or 60,000 revolutions per minute, faster than the turbines in any human-made engine. And yet, this is not chaos. It's one of the most stable rotations in the universe. These ultra-dense remnants are composed mostly of neutrons. packed so tightly that the entire mass of 1.4 suns fits into a sphere smaller than Manhattan. The escape velocity from the surface exceeds 0.5 times the speed of light. Even light struggles to escape the gravity well, emerging redshifted and distorted, but rotation adds another layer of complexity. It transforms the neutron star into a natural particle accelerator, with magnetic fields 1 trillion times stronger than Earth's. These magnetic fields funnel streams of charged particles along the magnetic poles. As the star spins, these jets sweep through space like the beams of a lighthouse. Each time a beam crosses our line of sight, we detect a brace, pulse, a perfectly timed flash of radio, X-ray, or even gamma-ray light. That's why we call them pulsars. They're not blinking. They're rotating, and their regularity rivals the most precise atomic clocks ever made. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University. She noticed a series of regular radio pulses repeating every 1.337 seconds. Far too precise to be natural noise. At first, her team half-jokingly labeled it LGM-1 for Little Green Men, suspecting it might be artificial. But soon, more pulsars were found across the sky, each with unique pulse periods but identical behavior. Nature itself, it turned out, had built these clocks. Each pulse we detect is a story of physics working at its limit. The magnetic field, locked into the star's dense crust, spins with it, generating powerful electric fields. These accelerate particles to near light speeds, creating a stream of synchrotron radiation that beams outward. The beam's alignment is rarely centered on the star's axis of rotation, so we see flashes only when it points toward us. A cosmic strobe flashing across vast distances. NASA's Chandra X-ray Observatory and NICE mission aboard the International Space Station have observed pulsars in multiple wavelengths, confirming that some rotate hundreds or even thousands of times per second. The record holder, PSRJ 1748-2446 AD, spins 716 times per second, completing one rotation in 1.4 milliseconds. If you were to stand on its equator, hypothetically, ignoring gravity, you'd be moving at 0.24 times the speed of light. Despite such speeds, neutron stars don't fly apart because their structure is dominated by gravity balanced against degeneracy pressure. Every neutron acts like a rigid element of a quantum lattice. To break that structure, you'd need to overcome the combined strength of nuclear forces across the entire star, something even this rotation cannot achieve. Instead, the star remains stable, spinning calmly through the dark. The magnetic poles act as enormous dynamos, driving current loops that release beams of radiation thousands of light-years into space. Some pulsars emit in radio frequencies, others in visible or gamma rays, and a few, like the Crab pulsar, emit across nearly the entire electromagnetic spectrum. That particular pulsar, born from a supernova recorded by Chinese astronomers in 1054, still spins 30 times per second, nearly 1,000 years later, its energy illuminating a nebula 11 light-years wide. The Crab pulsar's light shows something profound. Even in death, stars don't stop contributing to the cosmos. The energy from its rotation powers an entire nebula, heating gas and accelerating particles to near relativistic speeds. It's a machine that never needed design. Only physics. As NASA once described it, a pulsar is a lighthouse powered by gravity, magnetism, and the memory of a star. What makes pulsars even more extraordinary is their precision. Some, like millisecond pulsars, are stable to within a fraction of a microsecond. Astronomers use them to test the predictions of general relativity and even to search for gravitational waves. Networks like nanograv monitor dozens of pulsars simultaneously, using their tiny timing shifts to detect space-time ripples caused by merging supermassive black holes. In 2023, these collaborations announced strong evidence of a gravitational wave background permeating the universe. The low-frequency hum of cosmic collisions recorded not by lasers, but by pulsars themselves. This shows how these compact stars have become tools of precision cosmology. They allow scientists to measure distortions in space-time, test alternative theories of gravity, and refine our understanding of how galaxies evolve. Their consistency is so remarkable that some scientists propose using pulsars as a galactic GPS system. By comparing the timing of multiple pulsars, a spacecraft could determine its position anywhere in the Milky Way. A natural navigation grid written into the sky. But behind this elegance lies immense violence. When a neutron star is newly born from a supernova, its rotation and magnetic field can be chaotic. In just a few seconds, it releases as much energy as our Sun will emit in its entire lifetime. The magnetosphere, filled with charged particles, twists and snaps like a storm of invisible lightning. Such an object is called a magnetar, and its magnetic field can reach 10 to the power of 11 teslas. Strong enough to distort atomic orbitals and strip electrons off atoms 1,000 kilometers away. Occasionally, these magnetars flare, releasing bursts of gamma rays so powerful they can outshine entire galaxies for seconds. The most famous event, detected in 2004 from the magnetar SGR 180620, emitted more energy in 1/10 of a second than the Sun does in 100,000 years. Yet, after the burst, the star kept spinning, its rhythm unchanged. An unshaken clock amid cosmic chaos. It's in that quiet regularity that pulsars reveal something astonishing. Death, in the universe, often creates order. When the chaotic collapse of a star ends, the result is not randomness, but rhythm. A dying star, stripped to its core, becomes the most precise metronome in nature. Ticking across the void, marking time on cosmic scales. Each pulse is a heartbeat of physics, each rotation a testament to the conservation laws that rule everything from subatomic particles to galaxies. Even now, scientists continue to uncover new kinds of pulsars, some that switch on and off unpredictably, others that pulse in X-rays but not in radio. The James Webb Space Telescope, JWST, has begun probing the remnants around neutron stars, tracing how their winds shape surrounding nebulae and seed the interstellar medium with heavy elements. Each discovery adds another layer to the story, that even in extreme gravity and density, the laws of physics remain consistent, elegant, and knowable. So how can a dead star spin 1,000 times per second without tearing apart? Because its structure is defined not by fragility, but by balance. Between gravity's compression, quantum resistance, and magnetic tension, each of those forces is absolute within its scale, and together they form one of the most stable systems in the cosmos. In their stillness and speed, pulsars demonstrate the universe's ability to turn catastrophe into harmony. They remind us that even at the edge of destruction, nature builds mechanisms of precision. A neutron star may have lost its fusion, its light, its life, but it has gained a perfect rhythm one that keeps time for the galaxy itself. And if the story of spinning neutron stars teaches us anything, it's that motion and collapse are never the end. They're the beginning of new order. But what happens next, when that rhythm slows, when rotation weakens and the pulses fade? What remains of the star's enormous energy? Part 10. Could we exist without neutron stars? If neutron stars never formed, would life itself be impossible? It sounds like a question about distant astronomy. Yet the answer lies in every breath you take, every heartbeat, every atom inside your body. Because without neutron stars, there would be no oxygen to fill your lungs, no iron in your blood, no carbon to form the molecules of life. The story of how you came to exist begins not on Earth, but in the death throes of ancient stars. Every massive star ends its life in a violent collapse. A core collapse supernova. When the nuclear fuel in its core runs out, fusion can no longer counteract gravity. The outer layers fall inward at 1/10 the speed of light, slamming into the dense core. For a brief moment, the universe pauses between destruction and creation. At that instant, something extraordinary happens. The collapse halts. The reason? The birth of a neutron star. When the core's density reaches roughly 10 to the power of 17 kilograms per cubic meter, protons and electrons merge into neutrons, releasing floods of neutrinos. That sudden stiffening of matter, neutron degeneracy pressure, resists gravity's crush. The infalling material rebounds off the surface of this newborn neutron core, sending a shockwave outward. This rebound, amplified by neutrino energy, tears the star apart. It's this single moment, the supernova explosion, that scatters the elements forged during the star's lifetime into space. Without the resistance of neutrons, there would be no explosion, only collapse. The core would fall straight into a black hole, swallowing all its heavy elements forever. The universe would remain filled mostly with hydrogen and helium, the same simple gases born from the Big Bang. There would be no carbon chains, no water, no rocky planets, no life. As NASA once summarized, the iron in your blood, the calcium in your bones, the oxygen you breathe, all were cooked in the core of stars and scattered by supernovae. The physics that governs a neutron star is, in a sense, the blueprint of our existence. When the shockwave from a supernova races outward, it carries not only light but new matter. Elements forged in nuclear reactions under temperatures of billions of degrees. In the first seconds after collapse, lighter elements like carbon and oxygen form through fusion. Moments later, as neutrons flood the environment, rapid capture processes, what astrophysicists call the R process, build heavier elements like gold, platinum, and uranium. These elements owe their existence entirely to the conditions created by the neutron star at the center. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star collision known as GW170817. NASA's Fermi and ESA's Integral satellites simultaneously observed a burst of gamma rays from the same event. Within hours, telescopes across Earth, including the Hubble Space Telescope, turned to the source in the galaxy NGC 4993, about 130 million light-years away. Spectroscopic measurements revealed the unmistakable fingerprints of freshly forged heavy elements, gold, platinum, and lanthanides, more than 10 Earth masses worth, were formed in just a few seconds. It was the first time humanity had watched the universe making its own building materials. This discovery confirmed what astronomers had long suspected, that neutron star mergers are factories of the heaviest elements in the periodic table. Every ring, circuit, and planet owes some of its substance to such collisions. As Issa described it, the cosmos recycles its matter through death and collision, a cycle that began long before our sun was born. Indeed, our solar system formed about 4.6 billion years ago from a molecular cloud enriched by countless such explosions. When those atoms coalesced into Earth, the story of neutron stars became our own. Even the sun carries this heritage. Though it is an ordinary yellow star, its composition, about 2% heavy elements, comes from the ashes of earlier generations of supernovae. That 2% may sound small, but it's everything that makes life possible. Without it, Earth would be a world of gas, not rock. Water could not exist, and complex molecules could never form. Every leaf, every ocean, every living cell is built from matter that once belonged to stars destroyed and reborn through neutron physics. To appreciate the scale of this process, consider the energy released in a single supernova. In just a few seconds, it emits more energy than our sun will radiate in its entire 10 billion year lifetime. Most of that energy, about 99%, is carried away by neutrinos, tiny particles that barely interact with matter. Yet even the remaining 1%, converted into light and kinetic energy, is enough to illuminate a whole galaxy. Astronomers have measured such explosions reaching brightnesses of 10 to the power of 9 times that of the Sunday. At their peak, they outshine everything else in their host galaxies combined. Inside those seconds of chaos, new physics takes place. Shock waves churn through the collapsing star, triggering nucleosynthesis, the creation of elements through nuclear reactions. This process was first theorized in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle in a landmark paper known as B²FH. They showed that nearly every element heavier than helium could be traced back to stars, and that the most violent stages of stellar death, supernovae, were responsible for dispersing them. In their words, the elements of life are the ashes of ancient stars. Modern missions continue to confirm that insight. The Chandra X-ray Observatory maps the glowing remnants of supernovae, revealing regions rich in oxygen, silicon, and iron. The James Webb Space Telescope now peers into star-forming regions seeded by that material, showing how dust and gas recycled from older stars condense into new planetary systems. Each nebula is both graveyard and nursery, a reminder that the universe never wastes its matter. And at the heart of this cycle stands the neutron star. Without its dense surface to halt collapse, no rebound shock would ever form, no explosion would follow, and the heavy elements would remain forever locked away. The neutron star's existence is therefore the hinge between death and creation. As NASA's astrophysicist Jennifer Johnson once said, "Every atom heavier than iron tells a story written in the death of stars. That story is written in you." Consider the iron in your blood. Each atom once part of a star's core, fused in its final seconds, ejected into space, and later drawn into the cloud that became Earth, or the calcium in your bones. Born in the outer layers of a supernova, scattered, then reassembled billions of years later inside living tissue. Even the gold in a wedding ring carries the memory of two neutron stars colliding long before the sun existed. When you look at the periodic table, you're seeing a family tree of stellar events, each element the legacy of a specific kind of star. It's humbling to realize that the same physical laws connecting gravity, quantum mechanics, and nuclear forces also connect us to the cosmos. The balance that allows a neutron star to exist between gravitational compression and degeneracy pressure is the same balance that allows matter to organize itself into complexity. Without it, the universe would be silent and sterile. With it, we have diversity of elements, planets, and life. In this sense, the physics of neutron stars doesn't just explain their behavior, it explains ours. Even now, astronomers watch young supernova remnants, such as Cassiopeia A, whose light first reached Earth in the late 17th century. Inside its expanding cloud lies a faint point, a neutron star, still glowing softly in X-rays. Its presence proves that creation often hides inside destruction. As ESA described it in a mission report, when the star died, it gave back the ingredients for everything that would come after. So, could we exist without neutron stars? The answer, supported by every observation and every atom we can measure, is no. Without them, the periodic table would end near helium. The universe would have light but no structure, energy but no complexity, stars but no chemistry for life. Every mountain, ocean, and cell traces its origin to the physics that allows a neutron star to halt collapse. To the moment, gravity met quantum mechanics and rebounded into creation. And while neutron stars now spin quietly in the dark, their influence endures everywhere. Each time a supernova flares in another galaxy, it is the same story retold. Gravity builds, collapse begins, and then, against all odds, the universe finds a way to explode into life. From the death of stars comes the possibility of beings who can ask how they were made. If this journey has shown anything, it's that existence is not a single event, but a chain of reactions, each linked by the same physical laws, and at the center of that chain sits the neutron star. Small, dense, silent, yet essential. It is the reason the universe has color, chemistry, and consciousness. And as we close this chapter, remember, the light that reaches you tonight carries the signature of those ancient explosions, the echoes of the stars that made you. Because from the physics of neutron stars comes the chemistry of life itself, and from their collapse, our creation. Thank you, dear listener, for drifting through this long voyage of science and wonder. If this quiet journey brought you even a small moment of peace or curiosity, I'm deeply grateful you chose to spend it here. A gentle like, or a soft tap on subscribe, is the kindest way to let me know these night stories mean something to you. And if you'd like, tell me where in the world you're listening from, and what thoughts this journey left behind. Your words are the constellations that guide me forward. Until next time, rest easy under the same sky that once birthed the stars inside you, wishing you a peaceful night, a deep sleep, and the most beautiful dreams beneath the Milky Way.